All right, guys, we are finishing up with Lewis structures. So we kind of ended in a hurry last day. Hopefully you've looked at these a little bit and have kind of pondered over them. But if not, let's go ahead and do one. I want us to do carbon dioxide. I'm not going to give you the hints from the previous page until we do carbon dioxide, and then it'll go right along with what we're doing here, okay? So go to your page that gives you the rules. And I'm all about double-sided paper, but today it'd be nice if that one were single-sided, I think, because you've got to flip it back and forth. But look at the rules and tell me what you need to do for carbon dioxide. What's the first thing we do? All right, so find the total number of electrons. How do we find valence electrons? The periodic table groups tell us the valence electrons. If you're still confused on that, then my suggestion is go back to the electron configuration notation page where we did all the electron configuration notations. Find the biggest big number, like pick one that we did. Pick bismuth. We did bismuth, I think. So pick bismuth, find the biggest big number for bismuth. What is the biggest big number for bismuth that you wrote when you did electron configuration notation? 6. In other words, 6 is the what? The outer energy level. 6 is the outer energy level. How many valence electrons are in the 6th energy level? Well, if you look at your electron configuration notation, it says 6s2, 4f14, 5d10, 6p3. Do you see that? So how many are in 6? Only 6. 3 are in P and 2 are in S, so that's a total of 5. All right, if you go over here to the periodic table, how many valence electrons does this whole column have?
1, 2, 3, 4, 5.
So does bismuth have 5? And now you know why for some of you. The reason I'm going over that is because this morning there was somebody who still didn't get why we came up with the valence electrons that way. And so I wanted to confirm that. And then these would be what? 6, 7, and 8. Okay, except helium only has how many? 2. Helium has 2, and this whole F and D, rather, I did it backwards. But they have how many? 2 valence electrons. Good. 2. All right. So how many valence electrons does carbon dioxide have? Well, we have to write CO2 first. Then we say, how many carbon atoms do we have? 1 carbon atom. Each carbon atom has how many valence electrons? 4. Plus, we have how many oxygens? 2. Each oxygen has 6. So that's a total of 16. All right, that's the first rule or first step. What's the next thing? Pick a what? Pick a central atom. Pick a central atom. So who's going to be our central atom? Carbon is going to be the central atom. And what does it say to do with carbon? Single bond it to what? The other atoms. Does it say form single bonds to all the other atoms? With the central atom. So who goes in the middle? You just told me, but who goes in the middle? Carbon goes in the middle. And then what do we do? Just like that, yes? Is that making sense or not? Okay, then what do? We have to account We have to do some accounting. What are we doing? You subtract for the use of those. How many did we use? So we subtract 4. And that leaves how many left over? Then we place those 12 in pairs, giving them to the what? What's it say? Who gets those first? What's it say? Give them to the most electronegative atom first. All right, how do you know who the most electronegative atom is? It's oxygen. Now, how do you know that? There's 2 ways you know it. The easy way and then the remember way. What's the easy way? Look at your periodic table. Look at your periodic table, guys. It's on there. What does it say that oxygen's electronegativity is? 3.44. What is carbon's? 2.55. So is oxygen more? Yes. So we're going to place them around oxygen first because it is the most electronegative. How many did we just take care of? 12, and that's all we had left over. Now, before I finish this, I want to talk about why, or how rather, could you just look at the periodic table and do that? Well, electronegativity is how tightly an atom holds on to shared electrons. Who is going to hold on to the shared electrons more tightly? Someone who has 6 valence electrons or someone who only has 4? 6. Now, some of you are thinking, well, why wouldn't the 4 one do it? Because they need more. But think of atoms as being greedy and selfish. If they already have the most, are they willing to share much or as much? No. And so what happens is oxygen has more to begin with. So it's not willing to share everything with carbon. It's going to want to pull carbon's electrons to itself instead. And so it is the more electronegative. Another way to look at it is simply to say the trend was the same as what? It was the same as ionization energy. It was opposite of atomic radius. So if they get smaller going across, then the electronegativity gets greater, which means oxygen is greater electronegativity than carbon. So there's several ways to figure this out, several ways, but the easiest one's you got it on the periodic table, okay? Also, I want to make a note, just so that you will remember this, there is only one other element that is more electronegative than oxygen. Who is it? Fluorine. Fluorine is the most electronegative. Everybody else is less electronegative than fluorine. Oxygen is second most electronegative, which means it's either fluorine's the most electronegative or oxygen, and then everybody else is down below that. So anytime, this means anytime you have oxygen with anything, which is going to be a lot of the compounds and polyatomic ions we're drawing, anytime you have oxygen with anything other than fluorine, who's the most electronegative? Oxygen, okay? So that's not too hard to remember, and it definitely applies to a lot of what we're doing today. Now, going back to our drawing. Are the oxygens stable now? Are we done?
No.
Why not? Carbon does not have 8. How many does carbon have? 4. Now, there's 2 things you could do to make this stable, but there's only one thing that's right. What are the 2 things that could be done? Has anybody already figured it out? Where and how many?
2.
Make 2 double bonds is the right answer. She's correct. There's another option. And it still makes everybody have 8. You know what it would be? You could do a triple and a single would still make 8. Go ahead.
Why does carbon need 8?
Everybody needs 8 except for hydrogen. Everybody does. Because look where carbon is. Carbon is in the second energy level. The second energy level can hold 8. So it needs 8. Everybody past helium needs 8 because they have 2 energy levels. Okay? Good question. So what our thought process is here. We know that this oxygen's stable, this one is stable, carbon's not. So the first thing you do is you probably say, okay, I'm going to make a double bond. Now I'm going to go slow about this. Obviously most of you don't need me to do this, but I'm going to just go ahead and go slow to start with. So all I did here is I took out one lone pair, put it between the two. That didn't take it really away from oxygen, it's just now sharing. Does everybody realize what I just did? Since this is the first one we've done a double or triple bond on, I want to go slow on it. This means 2, 4, 6, 8, so this oxygen still has 8, but it makes this carbon have how many now? 6, and this oxygen still has 8. And so one of the potential choices is to say, well, let's just move another pair in the middle of these two, and that would make a triple bond. That means this oxygen still has them, and it would still make then carbon have 8. But I've told you that's not right. The right answer is make another double bond. So what we do is we put a double bond on each side, and that's our answer. And then I'll tell you why. Do you understand the process of sharing with who doesn't have enough from who has enough?
What about, like, does it matter, like, when you take them away?
Good question. Good question. I wanted, and I meant to do something goofy on you on purpose, but well, in a sense, I did. Do you see how it looks like I took this pair and put them in the middle, and then when I redrew it, I left the pair there, but at this time, it's this pair gone? It doesn't matter. What are electrons doing all the time? Moving. They're always moving. What you have to understand is what we're drawing right here is it's as if we went, bam, immediately, took a snapshot of it, and this is what it looks like right at that instant. And if it's at that instant, this is what it looks like. But the next instant we look like at it, it could be different. It does not matter. As long as you keep the same number and you always keep them in pairs. That's what matters. Okay? Now, the question of why does it form 2 double bonds instead of 1 triple bond and 1 single bond? And that goes back to how many does oxygen have to begin with? How many valence electrons does oxygen have? 6. And it is not willing to share any more than it has to, because it already has 6. So I'm going to write the hints down here, and these will help you. I'm going to write the first thing down. I hope you already know it, but I'll write it. Hydrogen only forms what? What kind of bonds? Single bonds. Hydrogen only forms single bonds. It cannot form anything besides a single bond. So hydrogen only forms single bonds. Chlorine, fluorine, bromine, iodine form single bonds only. And I ran out of room there, so I put only at the top. They form single bonds only. Sulfur and oxygen form single and double bonds. And nitrogen and carbon form all bond types. meaning they will form triple bonds. The last few years that I've been teaching, it's kind of interesting to me how much I learn as I teach. Or not necessarily learn, I relate, maybe. That's a better word to say. But one of the things that I relate chemistry to a lot, and I've seen it more and more as I've gotten older, is people. Chemistry and people, there are so many similarities between the two. And this is an example of that, I think. People, have you ever known someone who was just really poor, didn't have much at all, but they were the most generous people in the world? Have you ever known people like that? It's like you could go over to their house, maybe it was an older lady, for instance, and you could go over to their house and they would always be inviting you to sit down for supper and just sit down and, is there anything you need, honey? And they just, you knew they didn't have anything to give, but if they'd give you the shirt off their back. That is like the atoms that don't have very many valence electrons. Carbon and nitrogen. Carbon has 4 valence electrons. Nitrogen has 5. And they are saying, by being willing to form single, double, and triple bonds, they're saying, you know what? We will share everything we have. We're more than happy to just share it all. We'll just be happy to just share everything with you. We don't mind. We'll share it all. But sulfur and oxygen, they have more. They actually are a little greedy. Sulfur and oxygen say, we have 6. We have to keep 2 for ourselves, but we'll share 4. We'll make a double bond. Does that make sense? And then fluorine, chlorine, bromine, and iodine, how many do they have? How many valence electrons do they have? 7. But how many are they willing to share? Only 1. They're saying, I'm only going to share 1 with you. I'm only going to share to make a single bond. You're not getting these other 6 I have. You can have this 1 and we'll share. Isn't that funny, though? I mean, they're just like greedy, greedy people. They're very greedy because they will not form more than a single bond. They're going to keep them to themselves. Now, hydrogen is an exception in my scenario there. Hydrogen only has 1, but it can only form a single bond, because hydrogen can only hold 2 electrons, period. Okay? Is that your question?
Well, okay, you said a single bond is 2.
2 electrons sharing 1, basically. And I may have had my numbers off through that little scenario. In other words, fluorine, chlorine, bromine, and iodine have 7 total. So imagine 2, 4, 6, 7. And if they're bonding to something, they're only going to share this 1. Whereas oxygen and sulfur, they have a total of 6. So they will share up to 2 over here. And whoever else is coming has to bring 2, and that makes a double bond.
So like with the 7, where there's 2, and then 1, the other one that
Has to be,
has to come from somewhere.
yes, yes, yes. And bond to that, yes, yes. Okay? So then, this is the hints for how these bond. This is the hints. And if you'll kind of understand why they do this, that's why I went through the scenario of how many they have, then it's not so much memorizing the hints, it's understanding why they do what they do. So let's go back and keep going on these. Just because they can form a triple doesn't mean they will. I don't want you to immediately think every time you see nitrogen it's going to form a triple bond, because it's not. It will form single bonds, double bonds, or triple. Yes, ma'am?
When you're subtracting, like when you subtracted 4 from 16, how do you know
What you used. Because we started off here by using these 2. So you subtract what you used.
So do you always start with 6?
You start with single bonds between all the other atoms. Yes. Yes. Okay, nitrate. What's the formula for nitrate? What charge? All right, so NO3, -1. Now, a question I know you have that's related to the ion quiz today, as well as the way I wrote it now. Does it matter if you put -1 or 1 negative? It does not matter to me. Properly, it's 1 minus, but I'm not going to count it wrong if you put -1. Okay, so either way is fine. Valence electrons. We have one atom of nitrogen. It has how many valence electrons? Plus how many oxygens? How many oxygens do we have? 3 times 6, and I add 1 electron. Why do I add 1 electron? Because it has a -1 charge. Now somebody out there is wanting to say, where did it come from? None of this happens unless energy is present and there are other atoms that are in the area being willing to give the electron. In other words, you are not going to have nitrate formed unless there's some other metal or ammonium or hydronium present to give the electron. But don't worry about where it comes from. If that bothers you, just say there's an electron bank and it's available. And just think of it, it doesn't matter where it comes from. It's there. How do I know it's there? Because nitrate, when it's an ion, has a -1 charge. Okay? So total, how many do we have? What's my next step? Who's it going to be? Good. Then what? Single bond to everybody else. Single bond the central atom to everybody else. So we single bonded it to the 3 oxygens. Now here's where we have to do our accounting. What do we do here? You subtract how many? So you subtract 6 electrons because we used them. That leaves us how many? 18 electrons. Where do they go first? So 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes or no? Are we done? No. What's wrong? Nitrogen is not full. So what do? You make a double bond. And then the next question, does it matter where we put the double bond? No, it doesn't matter. Pick one of the oxygens and make a double bond. Pick one, move the electrons, and make a double bond. Rewrite it. When you get it rewritten, confirm that you haven't gained any extras. So 2, 4, 6, 8, that's correct. 10, 12, 14, 16, 18, 20, 22, 24, that's total. Yes? Then there's one last step when it's a polyatomic ion. You put brackets around the whole thing and you put a -1 charge. For this one, because it has a -1. You put the charge, whatever the charge is. That's the Lewis structure. Why do you put the -1 charge? You put the charge because it gained an electron, and we have to tell the reader of our structure that we added that, because this isn't nitrogen trioxide. Does that make sense? This is nitrate. And so you have to tell the difference between nitrate and nitrogen trioxide. Make sense or not? All right. You do phosphite. I want you to try phosphite on your own right here. Did everyone sign in? Nolan, are you here? Nolan Cook? It's amazing how you all showed up for an ion quiz. Is anybody else here from the 8 o'clock class? I thought there were 2 people, but I couldn't remember. Pass that down. What's phosphite? So that's 1 times plus. So that's a total of 26 electrons. Good? Anybody struggling on that part? All right, what's the central atom? And then what do we do? Now, someone might want to ask, does it matter if we put one at the top and not one at the bottom, or one at the, it doesn't matter. I just tend to do these the same way every time. It doesn't matter. So I took out how many? 6. That leaves how many left? 20. Now, if you're really fast in math, you immediately see what happens. Who's going to get them first? And that takes how many? So then what do we do with the last 2? You put them on who? Phosphorus. And then did that immediately make everybody happy? You don't have to do any double bonds at all. You don't have to do any triple bonds, nothing. Everybody's happy with single bonds. Now, there's one last step. What's that last step? Brackets and -3. All right, keep going. I want to just be quiet and let you do these. Just keep going and run through these right now. You doing them will be better than me showing you and you just redoing them. Okay? All right, it looks like most of you know what's going on, so let's see if you do. Ammonium is actually the easier one on here, really. If you know ammonium, what is ammonium? And that's 1 times, how many valence electrons for nitrogen? Plus 4 times 1. Each hydrogen has 1 valence electron. And then what do? Subtract 1 instead of adding 1, because it's a +1 charge, and that leaves us 8 electrons total. So then simply put your hydrogens bonded to your nitrogen. Did that just take out 8? And then what do we do to finish it? Brackets +1. Yes or no? All right, phosphorus trichloride. That's a compound. That's not an ion. It's a compound. How do you know? Because it doesn't say ion. It's a compound. It's a molecular compound. So what's the formula? And then 1 times 5 plus 3 times 7, and that's a total of how many? 26 electrons, and you don't subtract or add. What's the central atom? P. Good. Single bond to the Cl's. How many does that take out? 6. So that leaves us with 20. Have we seen this scenario before? You saw it. Yep. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. No brackets. Why are there no brackets? Because it's a compound. So that's it. Do you think that every one of the compounds or polyatomic ions that have 4 total atoms and 26 electrons will end up looking like that? Yeah, they will. And if you practice some of these on your own, you'll get into the habit of seeing these real clearly, and that's just like, oh yeah, and it's not hard because you start to see the patterns. Carbonate ion. Good. So that's 1 times plus 2, that's how many? How many again? 24 electrons total. So who is your central atom? Then you connect it to all the O's. Subtract how many? That leaves us with 18. Who's going to get them first? And then what? You have to put a double bond. Have you seen one like this before? Who was it? Nitrate. Nitrate. So you have to make a double bond. Now I'm going to be tricky. I'm going to put the double bond up there. Does it matter? No. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And there are 8 around carbon. Yes or no? And the last one, who is chlorate? ClO3, what charge? -1, good. Okay, so it's 1 times 7 plus 1. That leaves how many? All right. Do you already know what it's going to look like? So shouldn't be hard to do. Cl. That took out 6. That leaves you with 20. You immediately know how to put them. Yes or no? Is that making sense at all? Okay, you seem like it is. That's good. All right, now, before I leave this and go to the next part of this, I want to point out something, and I just remembered I didn't do something. I don't know if you ever do that or not. Remember you forgot. Sapling homework. In sapling homework, you have to draw some of these. And if you complain about sapling and their drawing, I'll let you use Connect next time. And then you'll really complain, okay? So don't fuss about sapling too much because it's a lot easier than Connect. But I think I put a training exercise on there for Lewis structures. Somebody's shaking their head, yes. Thank you. I thought I did, but I meant to look today and I forgot to look. Do the training exercise before you do your homework. Okay, that's why it's there. It doesn't hurt you to spend a few minutes on that because it will help you do the sapling homework better. So do the training exercise on Lewis structures, and then it won't be hard to put these in. I did not try to overload you with Lewis structures. And to be very honest with you, anytime if I were doing sapling homework, if it were me doing that homework, I would print out the whole homework assignment, do it on paper, and then sit down at the computer and plug it in. Now, some of you like to just sit at the computer, but I personally couldn't do it that way. I would have to print it out. But I would strongly encourage you on these Lewis structures, figure it out on paper. Then that way you're plugging in, it's just plugging it in. And you're not sitting there trying to think.
On some of the questions where it asks you to put like the element symbols and you have to capitalize them, it won't let me capitalize them. And then I get it wrong.
I'm wondering if have you updated your Flash player? Update your Flash player. Don't use Internet Explorer. Use Chrome or Firefox. Chrome seems to work better. And update your Flash player. Okay? I have seen that happen. I've had it happen before. And usually going to Chrome and updating the Flash player fixes it. If it doesn't, then call Sapling. Now, I want to tell you on Sapling, if you call Sapling, don't let them hang up until you get the problem fixed. Because somebody in my first class told me they called them, and I don't know who's telling me the truth, but the problem never got fixed, and then they fussed because the sapling, and I don't know whose fault it was. But my real urgency is to tell you, don't get off the phone until you've had the problem fixed. Say, I want to do one of these to make sure it's working. Okay? But that should work. Okay? All right, any more questions on these Lewis structures? All right, then let's go. We're going to finish up all of this with Vesper Theory, then I'm going to do nomenclature with you, okay? And then the last 10, 15 minutes of class, you'll have your quiz. All right. Vesper Theory. Vesper stands for valence shell electron pair repulsion theory. Now that sounds like a bunch of garbage, but break it down, and that's why I've written it out for you. Let's break it down. What is the valence shell? The outer energy level. So the valence shell simply means outer energy level. What's a pair of electrons? Come on, what's a pair of turtle doves? What's a pair of anything? Two. Okay. First, though, before we even talk about the repulsion theory, I need to know something. What charge do electrons have? They have a negative charge to begin with. So how can electrons exist in pairs? No, well, I'm saying, how do two electrons exist together? Opposite spins. Okay? So you get two electrons spinning together because they're spinning in opposite directions. So now what this is saying is we have a pair of electrons. They are existing in pairs because they're spinning in opposite directions. In our drawings today, we have shown these pairs with two dots, right? The two dots are a pair. The line is a pair. We've shown it that way. So the Vesper theory, valence shell, that's outer energy level, electrons, valence shell electrons that exist in pairs. So in other words, outer energy level electrons that exist in pairs do what to each other? Repel. Now, why am I standing here like this? What am I trying to show you? The electrons doing what to each other? Repelling, pushing away. Which means the Vesper theory is saying to us, electron pairs try to get as far away from each other as possible. That's what these electron pairs do. They try to get as far away from each other as possible. Because they do this, the shape of the molecule or polyatomic ion is different than other shapes, because different combinations of electrons do different things to each other in their repulsion. And this determines the shape of the molecule or the polyatomic ion, or it even determines the shape around a particular atom within the structure. We are not going to deal with the shape around the particular atoms. What we're dealing with is the shape of the whole molecule. Now, if you have this idea that really, why does it matter what shape it is? Let me explain it to you in something that I found this group usually understands better than I remember it for sure. Enzymes. Most of you have had a biology class rather recently or an anatomy class. Enzymes are specific for certain processes. Am I correct? Give me an idea of how your teacher explained that. If they explained it like I was taught, they used a pretty simple explanation. How did they explain that, how they work together, how they fit? What did they call that? A lock and key? Did anybody talk about the lock and key? In other words, the enzyme has a particular shape and it fits into this particular process because it fits there, because it's the only one that fits. It's like a key fits only the certain lock. That same kind of thing, right? So you understand that. Now go a step further and try to put all this together. What are enzymes made up of? Elements that make compounds. Aren't enzymes compounds? Yes. So elements are put together in certain shapes which fit this certain shaped molecule over here that they're working with. You follow what's going on? So does this shape make a difference? Yeah, this shape makes a difference. All of this, you can't have biology without chemistry. It all goes together. And so these 5 shapes that are listed on this sheet are the 5 shapes that you are going to be responsible for. Now, if you have had a higher level high school chemistry course, like an advanced chemistry or an AP chemistry, there was a possibility your teacher taught you even more shapes than these. And they probably went into depth with bond angles, hybridization, no telling what they talked to you about, and some of it seemed pretty Greek. I have broken this down simpler than simple. It is so specific, this should not be hard at all to understand these shapes, because I haven't made you learn bond angles. We're looking at this from kind of just an absolute elementary level, like triangles and squares and things like that. That's how we're looking at this. So I'm expecting you to know the 5 shapes, and these are the 5 shapes that I want you to know. Linear, bent, trigonal planar, trigonal pyramidal. I don't know why I didn't bold it and underline it, but it is another shape. And tetrahedral. These are the 5 geometrical shapes that we are going to learn. So what I have done on each of these is I have been extremely specific and told you exactly what to look for so that you can get these shapes correct. So linear may contain 2 to 3 atoms, may have single, double, or triple bonds, but it will have no lone pairs of electrons around the central atom. What's a lone pair? 2 electrons that are not bonded to anything else, okay? So they're by themselves. That's a lone pair. So the key to linear is the no lone pairs. That's the key to linear. All diatomic molecules are going to be linear. Now that's like a duh. We all should say that on that one. What's the shortest distance between 2 points? A straight line? So if you have H-H or O double bond O or any of those diatomic molecules, are they going to be linear? Yeah, there's no central atom. There's nothing to bend them. They're all going to be linear. So all your diatomic molecules are going to be linear. And then I'll list for you carbon dioxide. So what I want you to do is I want you to have this in front of you, go back over to this page that you did all the drawings on, and find carbon dioxide and look at it. And tell yourself, why is it linear? Why is carbon dioxide linear? Who's the central atom? Carbon. Are there any lone pairs around carbon? Not at all. Not at all. Guys, this is like carbon dioxide. This is C. What are these? Double bond. I said it wrong, didn't I? This is O. Sorry. This is O, double bond, C. And then is there any lone pair here? Is there any lone pair here? No. So why does it stay linear? Because there's nothing here or here or here or here to bend it. Does that make sense? There's nothing to push. Because what's happening to these two bonds, are they pushing as far as these are pushing and repelling against each other? So that's going to be linear. It's going to be straight. It's going to be linear. So carbon dioxide is linear. I would, if I were you, write on this sheet where you have the drawing, linear. And then later go back over here to this sheet and draw carbon dioxide so that you have that visual both places. So right on here, linear. And then later come back and draw carbon dioxide on this paper. Bent. Bent will contain 3 atoms. It can have single or double bonds. And it will have 1 to 2 lone pairs around the central atom. And so I wrote for you water. Find water in your notes. What do you see with water? Do you see the lone pairs? Now, here's what's crazy about this. For a couple of days, I've stood up here and said, okay, I'm water. And if you just take my hand to my hand, is that a straight line? Yeah, so you're thinking, well, it's linear. In fact, I drew it in a straight line, didn't I? But now we find out that, yes, this is a single bond. Yes, this is a single bond. But what's up here? A lone pair. What's down here? A lone pair. And you have to remember, we're not planar. We're not flat Stanleys. So what are these two, what's this lone pair doing to the lone pair here? It's pushing away and repelling, and then these are doing what? They're repelling, and so it ends up, it's not linear, it's bent. So this bond actually gets bent. And if you want to, you could say it's like this, because again, it's 3-dimensional. It's not flat. So it's bent down. Somebody asked me this morning a really good question. They said, doesn't this lone pair, though, even out this lone pair? No, the lone pairs do not even each other out. Anytime you have a lone pair around a central atom, it actually bends those bonds. It's almost like it's more powerful than the bonds themselves, and it will bend them. And that happens, you're going to see that happen again. Anytime you have a lone pair around a central atom, the bonds get bent. Okay? And so that's what causes water to be bent. So on your paper, I would put bent next to water. None of the rest of these are either bent or linear because they're all more than 3. And so you'll have to do some on your own to get some more. But you can find those on your ion sheet. If you drew some of the ions, you could find that. So let's go to trigonal planar. Trigonal planar, I have written this one so specifically it's almost sad. It contains 4 atoms. It will only have what? Single bonds. And what does it not have? It has 2 single bonds, rather. I lied. I said it only has 2 single bonds, and then it has what? 1 double bond. And what does it not have? What does trigonal planar not have? That's the key. And then I put on here nitrate ion. So go back over here to your paper. Do you see nitrate ion? Does that fit? What do you see? 2 single bonds, 1 double bond. Is there a lone pair around the central atom? No, there is no lone pair around the central atom. No lone pair around the central atom. Now, some of you are saying, but yes, there are lone pairs. I agree, there are lone pairs. But what's important? The central atom. It's the lone pairs around the central atom that's important. That's what we have to pay attention to. Some of you also say, but you drew this more like a T. I did draw it like a T, but that doesn't mean that's what it looks like. I drew water like a straight line, and it's not a straight line either. That's just how I draw them. This one is the funniest one. Throughout the years I've been doing this, I've had one student get mad at me for saying what I am when I do this. But you'll remember, don't call it this name. It's trigonal planar. But if I said to you, I'm a single bond, double bond, now tell me, put a ponytail in my hair and a smile on my face, who am I? A cheerleader. Everybody knows that. And I had a cheerleader one time get mad at me. She got offended by the fact that I said that. And then I always will say, too, this is hard. If you think being a cheerleader is easy, just standing here with your arms up like this is hard. It's like it gets tiring up here when you stand like this. So why do I do this, though? Because what I'm trying to show you is, and I'm sure I look stupid, but this angle is the same as this angle is the same as this angle. Now, I'm not expecting you to know bond angles, but my point being, is there any lone pair here or here, anywhere, that's pushing these differently? No. So the repulsion theory says the angles are the same. That's what the repulsion theory says. Now, who else is trigonal planar that you've drawn? Carbonate. Right here. Carbonate. This is trigonal planar. So we have drawn 2 trigonal planar. One of the reasons for showing you the trigonal planar body-wise is because trigonal pyramidal makes a lot of sense when you've seen trigonal planar. I will call this oftentimes trigonal pyramidal, but if you look it up, it's actually trigonal pyramidal. It is 4 atoms, but the difference between trigonal planar and trigonal pyramidal is what? Trigonal pyramidal has what? A central atom with a lone pair and only single bonds. Whereas trigonal planar had no, what? Lone pair. So now, this is the funny one, and I'm not going to do this one, but this is the funny one, but you get it by just the visual of it. If I stood like this, but then I said this is a lone pair, what is that lone pair going to do to these bonds? Bend them. And if I went all the way down, what do I look like? A pyramid. Does that make sense? So that's why. That lone pair pushes these and causes it to look like a pyramid, which is why it's called trigonal pyramidal or trigonal pyramidal. Now, we did not draw nitrogen trifluoride. So quickly draw nitrogen trifluoride in that space. And then you're going to go to your notes and find a trigonal pyramidal. Is that what you drew? Yes or no? Okay. Who else on the drawings that you have is trigonal pyramidal? Phosphorus trichloride. So down here, phosphorus trichloride is trigonal pyramidal. Who else? Phosphite and chlorate. That's right, we have a ton of these. Ton, 3. Several. Does that make sense? You see those? Okay. Something I want to point out, I'm hoping some of you saw this and thought, well, yeah, I know that. And if you didn't, I'm going to try to point it out so you will. With nitrogen trifluoride, you can't see that. Nitrogen trifluoride, you had 5 for nitrogen, 3 times 7 for fluorine, and that made the total of 26. Phosphorus trichloride is the same. Did you catch that before you started doing it? Really doing it? Did you like look up there and say, look, nitrogen and phosphorus are what? Same family. Fluorine and chlorine are in the same family. Does that make sense? And all the numbers are the same. So would it make sense they would look identical? So if I said to you, draw, not that we're going to, but if I said draw arsenic triiodide, would it look just like that? Does that make sense? Okay. All right, the last one is tetrahedral, and it is really the easiest one because it's the only one that has 5 atoms. So if you have 5 atoms, it's going to be tetrahedral. I'm not giving you any other choices. So if you have a 5-atom molecule, it's going to be tetrahedral, but let's look at it. It has only single bonds, and it has no lone pairs around the central atom. Draw methane, CH4. Draw that. Methane does not have a charge. Methane is natural gas, by the way. If you ever want to know what your natural gas is at home, that's methane. Your Bunsen burners in labs burn on methane, or burn methane. So that's what you should have for methane. Who looks just like that? Ammonium ion, except ammonium ion has a charge. The charge doesn't change the shape, though. So on your paper under ammonium, I would put tetrahedral. Put tetrahedral. Now then, I know most of you are not really listening. You're studying your ions. So you've got the sheet handy. Go ahead and tell me, starting on the -3 column, who will have a tetrahedral shape? Phosphate, arsenate. Now go to the -2 column. Chromate and sulfate. You with me? Oxalate has 6 total atoms. Okay? All right, go to the -1 column and tell me who will be tetrahedral. Permanganate could be, should be, looks like. Keep going. Perchlorate. Hydrogen sulfite. Do you see those? So anytime it has 5, that's what you're going to find. Okay? Sulfite, hydrogen sulfite, because you put the S in the middle. H on one side and the O's on the others. Okay? I would strongly encourage you to practice Lewis structures using your ion sheet and draw them just like we've been doing. Draw some of the ones that have 3 atoms because those are some that need the hints. Like thiocyanate, SCN -1, there's a lot of electrons in there that you've got to figure out where they go. OCN is another one. So try some of those, and I think it will help you if you do a few on your own like that. The central atom, it's on your rules sheet, but it's the least electronegative. Carbon, if it's involved, usually will be a central atom. Yeah. Carbon's usually the central atom, if it's in there at all. Okay, so let's now go to nomenclature. Looking ahead, I want to just kind of show you what's going to happen on Monday. Your test is Wednesday. It's been on the schedule. Your test is the 27th. Which is next Wednesday, a week from today. We only have 2 pages of notes. That's it. That's all we have left are 2 pages of notes that are actual new material before your exam. Today, I want to go over a little bit of nomenclature. I'm hoping in my discussion with nomenclature with you that it will spur you to study a little bit this weekend, rewatch or watch the videos if you have not. And guys, I want to tell you something. On the videos for nomenclature, if you say those are absolutely terrible, please do something different, tell me that. You're not going to hurt my feelings. Tell me and say, do this. This would be helpful to me if you change this about it. Tell me those things. If you feel like those are not beneficial to you, you've got to tell me these things, okay? So let me know if they're not working for you. The plan for Monday. The plan for Monday is to finish this. We're not going to do all of these today. We're going to go through today to get you kind of in the mode so that you can spend more time on your own. Then we will finish this Monday. If I feel like we need more practice, then I will probably come prepared with more practice to give you so that we can spend more time on it. If you are of the opinion that you can listen to me in class, watch the videos, and do great on the test, I would do at least 2 more worksheets. Okay? Nomenclature is one of those things that's going to take time. It doesn't just happen overnight, because here's what many of you are doing right now when you practice nomenclature. Your ion sheet is sitting right here next to your paper. And what ends up happening lots of times is you can take the ion quiz tonight and you can do okay on it. But then, when you're doing nomenclature, you use that ion sheet and you don't think. So then, if I were to give you just a blank one of these without an ion sheet, you would go blank. Because you had used this crutch so much that you really can't put it with this together. So practice. There are like at least 3 or 4 other nomenclature worksheets on Blackboard. Take a nomenclature worksheet, have a periodic table only, put your ion sheet away. Try to do it. Then check yourself with the answer key on Blackboard. And then what you miss, then that tells you really don't know those ions if you missed them. Okay? I didn't tell my morning class this, and I should have, and I'll try to do this Monday. I have students who tend to think, well, it's going to be multiple choice, so why am I worried about it? And I agree, it is multiple choice, but I'll be honest with you, I have found students do worse on it being multiple choice because I don't give partial credit, and the answer choices that I give you are definitely things that you might think are right. Because I'm going to answer every answer choice as something a student might think it is. And so if you really don't know what you're doing, you're going to pick an answer that's not the right answer, or you might just get lucky, but your chances 1 out of 5 that you're going to just guess the right answer. That's not very good odds. Okay? So you need to learn how to do this. This test number 2 typically has the lowest test average. Okay? If that helps you study any. I'm not making that up. Typically, test 2 is the lowest test average of any of the 5 tests. So that hopefully gets you realizing you've got to spend some time. I think a lot of it's because of the nomenclature. Because I think that people, they really don't know the ions, or they can, I think people put it in short-term memory, just like some of you have done all night tonight. You haven't paid a bit of attention to me, many of you. You've had your ion sheet out and you're paying attention to ions because you're thinking, I got to get those 10 extra credit points. But, you know, you may make a 60 on the test. To me, who cares if you got 10 extra credit points if you really didn't know what you were doing? And so what happens is they memorize them, short-term memory. Hurry up, get that quiz out of my way. I'm going to get those points. Oh, I don't have to worry about it anymore. That's what I think. Because when you look at what we've been doing, none of it's hard. I mean, electron configuration notation, man, you all got that. You got Lewis structures, or you seem to tonight. Vesper theory is not hard. Protons, neutrons, electrons, none of it. So I don't know. I don't know if it's the amount of material. I don't know why. But I do think part of it is nomenclature. I think people just don't take it seriously.
One of the practice worksheets, when I click on it, it shows up in really small letters and a ton of squares.
You know what? I think I know which one you're talking about, and for some reason that loaded as an HTML file, and the squares are supposed to be lines.
But it's still so small.
Can you still read them? Can you enlarge it?
No, I couldn't.
Like when you print it, can you go to print the screen so it's super tiny? Try to print the screen and then just do it on another sheet of paper. Okay? Or print out the answer key and cover it up. Okay? I didn't know it printed that small. I knew it had the squares, but I didn't know it printed that small. If you'll tell me which one it is, send me a picture of it, circle it, and send it to me in email, then I'll try to go in and fix it. Okay? But in the meantime, just print out the answer key and cover it up, or print that out and cover it up. Okay? All right, so I will also probably go over acids. This is where people have a lot of trouble usually, and I want to talk about them tonight, but Monday I've got that to go over if we need to. So what did I tell you? What did Video Me tell you? The first thing I would do is what? Label. I would label these. That's what I would do. I would label these. So I'm going to put a line here, and we're going to do these. So I'm going to label these. I need a periodic table out. Just a reminder, for the purpose of nomenclature. For the purpose of nomenclature. For the purpose of nomenclature, this area that I have put the red around, this area is called transition metals for the purpose of nomenclature. Meaning anything between these points except aluminum, zinc, cadmium, silver will need a Roman numeral and can have a different kind of charge. Or if it doesn't use a Roman numeral, it will use the us or ich name. Everybody follow me? Okay, that's our rule. It's not this for transition metals, it's actually here. I want to point that out. Okay, so let's start at the top. What kind of compound is potassium sulfide? Ionic. And it's just a plain Jane ionic. Potassium has a fixed charge. So it's ionic. Calcium bromide. Magnesium phosphide. Say it again. Good. Carbon monoxide. Molecular. Barium oxide. Ionic. Now, some people are like, how do they know that? Well, if you watch the video, you should know it. But if you didn't watch the video, is this a metal? First column? Metal, second column? Metal, second column? Non-metal, non-metal? Metal, second column. Follow? Okay. Disulfur decafluoride. Non-metal. So what is it? Molecular. Nitrous acid. It's an acid. And what kind of acid is it? It's tertiary acid. Now, how did she know that quickly? It does not say hydro. If it does not say hydro, that means it's a tertiary acid. If it says hydro, then that means binary. So this is a tertiary acid. Hydroiodic acid is a binary acid. And then on this side, anytime you see AQ, what does that mean? Acid. So then you have to say, what kind of acid is it? It's a tertiary acid. How do you know? Because it's a polyatomic ion. If you didn't recognize it's a polyatomic ion, you should at least see 3 different elements, and that's tertiary acid. BaSO3, ionic. How do you know it's an ionic? Because barium is an ion, or barium is a metal, and that's how you know. What is this one? Tertiary acid.
Can you think about it because 3 is like tertiary?
Yes. Yes, that's why it's named that. Yes. Her question was, can you think of that as ter means 3, and that is exactly why you think of it. That's why it's called that. Because 3 or more means it's tertiary. That's where that's coming from. All right, what kind of compound is this? It's a transition metal ionic. Lead is in the middle, so I put Ti. SrNO2, 2. People don't know what Sr is my experience, and so they get confused there. But it's strontium, and that's simply a metal compound, or it's a metal in the middle, or in column 2, rather. So that's an ionic. H2Cr2O7, tertiary acid. HiO3, tertiary acid. SO2, molecular. Molecular. Why? What is this? I'm not saying name it. What kind of elements are these? 2 nonmetals. Now, I want to go somewhere on here just to show you something. What is this? What kind of compound is this? No, and I'm glad you said that. I pulled you in my trap. It's molecular. Now, here's where you're confused. But today, that's sulfite. Here's where you have to understand what's going on. What does it say at the very top of this? That means this whole page is what? Compounds. Now, with that said, let me go a step further. Today, on this quiz, is the only time I will ever give you a polyatomic ion and have you spit it back out at me. Never again, not on your test, never again will there just be an empty ion that I say, name it, or write the formula for an ion. Because the whole thing is ions aren't formed unless they have something to form with, which makes a compound. I'm only having this ion quiz is so that when you see SO3 with something else, or Cr2O7 with something else, or NO2 with something else, you know what that is. Does that make sense? So never again after today will you have an ion that you have to tell me what it is. This is the only time. Okay? So let's go back to the top here and do these. We're going to actually go across the page now. If it were me, this is what I would do. I'm doing this as if I'm the student doing it. I've already told myself it's ionic, so then I put charges because I need charges on ionic. So what's the charge of potassium? Sulfide? -2. And then if you want to crisscross, use that method, that's fine. I'm hoping you understand what the purpose of crisscrossing is. It's to do what? To make the charges balance, to make the positives equal the negatives. So what do you need to do? K2S. Why? Because 2 times +1 is +2. Does that balance out the -2? Yes. All right, go over to this one. I have told myself it's a tertiary acid. That means that it has a polyatomic ion in it. Who is the polyatomic ion? Oxalate. Then I say, if it's a tertiary acid, it does not say hydro, but my ending of the ion, if it's 8, changes to ic. If it's ite, it changes to us. So I don't say hydro, but I know this is oxalate, so the name is, it's actually oxalic acid. And then usually somebody says, she is just making this stuff up. And I would think so too if I were you. So now your job before Monday, go to Walmart, go to the cleanser aisle. You'll have paper towels and Kleenexes at your back. Face the cleanser aisle. Go down to the bottom with the canister cleansers and find the one labeled Barkeeper's Friend. And you will find out that oxalic acid gets rid of rust on stainless steel. And it's in that that cleanser. So you'll find it's true. I'm not making these up. Okay? It works well. All right, calcium bromide. It's an ionic compound. What's the charge of calcium? Bromide. So what's the formula? CaBr2. Yes? This is an ionic compound. This is just simply a matter of knowing your names. Barium sulfite. Barium sulfite. If you don't know your polyatomic ions, you call that barium sulfur trioxide. And that's wrong. That's why I want you to learn your ions. That's what you might... No. No, I'm just... But that's what I see on papers a lot, stuff like that. Because they just start naming things. Yeah, no.
I was like, what was that?
Where do I find that? All right, magnesium phosphide. Go ahead.
How come you don't change those to I? You know, you change the ending and all the...
Go back to your, I'm not being mean, I just want you to, you'll remember it if you have to go look. You have a periodic table that has charges on it. You got it handy? Do you have charges on there? What does it say on that non-metal side over there? Up at the top? So those non-metals become negative, and you change their ending to "ide." Those are the only ones you change the ending to "ide." The metals, we don't change their ending. And the polyatomic ions are named what their names are. So we don't change their names. So if it's sulfite, that is the name. If you wrote sulfide, then who are you saying this is? Just S. Okay? Something that I think may have helped a student this morning to think of it, think of the polyatomic ion name as like your name. So if your name is John James Jones, that's your whole name, John James Jones. Your initials would be JJJ, or you could put J to the third. That's like your formula. You follow what I'm doing? So SO3 is like the formula or the initials for sulfite. That's the same correlation there, if that helps. Ionic, what's the charge of magnesium? Phosphide. So what's the formula? Yes or no? All right, H3PO3, tertiary acid, you told me. Who is this? Phosphite. So we name it how? And it is actually phosphorus, and somebody may say, well, what if I just call it phosphus? Because your rule says 8 changes to ic, 8 changes to us. Guys, if you wrote phosphus, I'd count it right. You obeyed the rule. But truly, it's phosphorus. It's phosphorus. All right, carbon monoxide. That's a molecular. You simply write the symbols by what they're telling you to do. CO. 1C, 1O. Yes? This is probably one of the harder kind, right here. This is where students usually mess up. Why? Because lead could be lead 2 or lead 4. So you have to figure out which lead it is by looking at the anion. What is chloride's charge? It's always -1. And you have 2 chlorides. That makes it a total of -2, yes? So what must this lead be to balance out the -2? You only have one of them. So the name is lead 2 chloride or plumbus chloride. Now, today, if I gave you a transition metal symbol and charge on the quiz, let's say that I gave you Cu plus 1, then you could call that copper 1 and you're correct. Or you could call it cuprous and you're correct. Don't call it cuprous 1. That's wrong. It's either copper 1 or cuprous. If you put copper 1 or cuprous, that's double correct. No, you don't get 2 extra points, but it's correct, okay? But you can just pick one.
Well, that was the same for the exam.
Yes, but it's multiple choice, so you're going to know by looking at the choice, and I would not give you, there will never be 2 right answers.
But on the quiz, would you write bicarbonate and then also hydrogen, whatever?
No, her question was, will I write bicarbonate and hydrogen carbonate so that you see the same? No. If I wrote bicarbonate, you have to know what it is. If I wrote hydrogen carbonate, you have to know what it is. Just like if I wrote ferric on the test, you have to know what it is. I'm not going to put underneath ferric, oh, this is iron 3, by the way. Yeah. It has to be spelled so I can read it phonetically. I'm a phonics reader, so if I cannot read it phonetically, then what I'm saying is, if it doesn't sound right,
Yeah, just sometimes it's cuprous or whatever.
cuprous, you put O-U-S and sometimes just U-S, and I'm the same way. That's fine, because phonetically it's still the same. Same like chloride, if you put C-L-O-R-I-D-E instead of C-H-L-O-R, I would count it right. Okay? All right, barium oxide. What's the charge of barium? Oxide? So what's the formula? Okay. What is this one? nitrite. Strontium nitrite. Disulfur decafluoride. Guys, there's no crisscrossing. It's what it is. So what is it? S2F10. Deca is 10. Do you reduce? No, not on molecular you don't reduce. No. No. Tertiary acid. Who is the polyatomic ion? Dichromate. So how do I name it? Dichromic acid. Yes or no? Nitrous acid. What kind of acid is it? Okay, how do you know? Again, doesn't say hydro. So what did nitrous come from? 8-ic, us. So who did it come from? Nitrite. So what I do is I write nitrite down, and then I say, what charge does nitrite have? -1. So how many hydrogens go with it? Only 1, and then AQ at the end. Yes? No, AQ means acid. HiO3AQ. It's an acid because it says AQ. You've already told me it's tertiary acid because it has a polyatomic ion. Who is this polyatomic ion? Iodate. So then iodate changes to iodic acid. I purposefully put these near each other to show you the difference between a binary and a tertiary that are similar. Hydroiodic acid. Tell me what hydroiodic acid indicates. It's a what? Binary acid. All of the acids have hydrogen. But this is saying by writing hydro, it's saying it's a binary acid, which means it's hydrogen and whoever else it is, who is it? Iodide. And iodide has a -1 charge. Hydrogen is +1. So AQ. Now look at these. Look at these and see. Hydroiodic HI, iodic HiO3. Do you see the difference? Hydro actually has less letters. You say a longer name, but it's less letters. Okay? And then this one, sulfur dioxide. Sulfur dioxide. Does that help any at all? Were there any questions on this that you had that you didn't understand on this? Go ahead. Lithium carbonate. Yes, I see it right there. Okay. That is what kind of compound? What is it? Ionic? What's lithium's charge? +1. What's carbonate's charge? -2. So how many lithiums do you need? So Li2CO3. And no crisscrossing, really, because this 3 goes with that O. Okay? Any others on here you need to see? Sure. Guys, be quiet and let's listen to the question.
On chromic acid, so because chromate has a -2 charge, that's why there would be H2.
That's exactly right. Her question was on chromic acid, why is it H2? Guys, look at this one because I'm not going to do it Monday. On chromic acid, why is it H2? As she was talking, I was writing, and she said, chromic came from, say it, chromate, so I wrote chromate. And then she said chromate has a -2 charge, so I said it has to have 2 hydrogens.
So as a way to remember that you need to, could I put like an H in front of it and kind of like think of it as a crisscross?
You could, what I would do if I didn't want to write it here on the line to start with, when I saw this, I would put CrO4 -2 and I'd put H plus 1.
Okay, that's what I just put the H out to the left.
Yes. 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 I don't, if I were grading this by hand, my rules when I graded this by hand, I don't care what you have over here. What is here is the final answer. Don't put charges here. But over here, absolutely write all over it. Same thing here, write all over it. Okay? Other questions? All right, we're actually out early, done early.